Hi, thank you for having me to talk about Rust and IT sustainability. I present myself very briefly. I'm Benoit Petit. I'm an IT engineer, but let's say my work shifted a bit a few years ago. Now I'm more like an open source developer and a consultant in IT sustainability. I co-founded Hubblo, which is a company working especially on those topics, building open source software to help to evaluate the impact of ICT on the environment. And that does consultancy as well. And of Boa Vista, which is a non-profit. And we will talk extensively about Boa Vista today. So regarding Hubblo, in like 5 seconds, we build open source software to help evaluate the impacts of ICT on the environment. We do consultancy and studies for governmental agencies, and we do some open research and development, including topics like the indirect effects of ICT on the environment, which is a huge topic, not so documented today, or things like what are the impacts of ICT at the scale of a region or a city or that kind of thing. And regarding Boa Vista, which is, as I said, a non-profit, it's a non-profit that gathers more than 160 members now at the last count. The idea is to bring together people from both the private and the public sector, companies, researchers, universities, freelancers, actually anyone who is interested in working on those topics and helping us to work on open data sets to help with evaluation, methodologies to evaluate the impact of on-premise infrastructures or cloud or IT services in general, or who are interested in working on open source tooling to help with that as well. And you'll see during the presentation, when I talk about a project that's born in Boa Vista, there will be the little logo on the bottom right to say, to mark that it's a project from that we work on in Boa Vista and not just in Europe. So when we talk about the Rust and we think about IT sustainability, a reflex that comes at first could be to say, are there benchmarks anywhere that tell me if Rust does good in terms of performance, low resources consumption, maybe low energy consumption and that kind of thing. And as you may have guessed it, there are some benchmarks. There is one from Portuguese researchers that has made some noise like 6 months ago or maybe 1 year ago. Actually, it's older than that, but because they publish every year a new version, every time it makes some noise. So it's called Energy Efficiency Across Programming Languages. It's based on the computer language benchmark game, which is a fixed set of algorithms that you can find on Wikipedia. And it's just a comparison across all those algorithms between the languages. So as you guessed it, it's based on fixed tests because the algorithms are defined in advance, and there are no other real variables in the test. But anyway, what we can see in those benchmarks is that Rust most of the time is pretty well ranked in terms of energy, time to complete the task, memory consumed. Most of the time it's in the top of the rank, not always at first. In many cases, C or C++ could do better, but it's still in the top 3 or the top 5, depending on the test you will look at. And if you look at the aggregated results, it's still good. Rust is in second position in energy and time, only in sixth position for memory. But anyway, if we look at the overall result, it's pretty good. So that's the first approach to that. And starting from this point, we could think, okay, it's great. I just have to code in Rust to lower the impact of my work or of my service on the climate and on the environment. To my opinion, we should not go so fast and remember that the choice of the language is just one part of the software architecture. And that's in this idea that there is another benchmark that has been published. This time it's made by some of my colleagues at Boa Vista, fellow members, Yoon and Jeremy, and other contributors since, but they started the project in the beginning. And in this benchmark, they included other architectural choices, compilers, interpreters. So for example, on Python, you could run on the default interpreter, or there is PyPy3, or there are other interpreters. That's one of the variables. Languages, of course, databases. So far, I think they only have compared with PostgreSQL and MySQL. Caches, whether or not there is pagination or not in the app. So yeah, sorry, the basis of the benchmark is a to-do list application and API that's implemented differently with those different choices. It's on GitHub, so you can have a look and try it, fork it, and propose changes, of course. And if we look at it, so here is a very summarized version of the results that's much more complete and precise and detailed than that. So I really encourage you to either attend to one of Yoon and Jeremy conferences or have a look directly at the project to have a more precise idea. But if we really summarize it briefly, here the green squares, they represent a set of results with different architectural choices and stacks. So, for example, behind PHP, there is not just, okay, we changed the language for PHP. There could be several results for, we changed the ecosystem, we changed the database, we changed the cache, but just it's an aggregate because all of those tests have a common denominator, which is PHP. That's the same for the other green squares. But anyway, if we summarize it this way, which is a bit abrupt, but still, we still see that Rust does pretty good in terms of energy consumption by iteration and in terms of performance, at least. It's pretty close to Go, we can see, but still good results. So at this stage, what they realized is that they could try to rank the architectural choices that have the most impact. There are other slides on that, of course, in their presentation. I just took the largest impact that they identified with this data set. And so the language, or more likely its ecosystem, and I do think that the ecosystem word is very important here because, as I said previously, for example, in Python, I remember that there are huge differences between running, for example, Python 3 on the default interpreter and running Python 3 on PyPy3, for example. So it shows that it's not just a question of language, but also how you run, how is your runtime, what are you using behind the scene. So this is one of the large impact choices according to the current state of this study. Database choice is also seem also pretty important. And of course, whether or not the code is of good quality. So yeah, those are the three items that they emphasized. But still here, we realize that going for Rust might be a good choice. I said it previously, but of course, that's an open source project. So you are really encouraged to raise issues on their repository and contribute if you're interested. And part of Boa Vista Studies, you may find more information on our website as well. And yeah, tip for the next EuroRust event, maybe next time you could invite Yoon and Jeremy, because their presentation is very, very detailed and very interesting. At least it was very interesting to me. So again, at this stage, it still seems great as a Rust developer. So far, so good. We only have good signs that Rust is still a nice choice. Spoiler alert: this won't change, but just we'll try to have a wider view than just this question about language. Before that, to clarify also my relationship to Rust, one of maybe the first approach for me about environmental impacts of HCT on the environment, it was, okay, what's the energy consumption of my server? What's the energy consumption of my software? That kind of things. I had in mind already at that time, even if I didn't know the benchmarks, that Rust allowed for performance and low resources consumption. So I went for it. When I tried to evaluate this energy consumption, so I started a project to measure the energy consumption of servers and the applications running on the servers. And of course, I did it in Rust. So the project is named Scaffold. It's an open source project, of course. It has now about 15 active contributors, I guess. And it runs in several companies' machines that are very good contributors for us. To clarify what's the role of Scaffold in the monitoring stack, it's just a data collection tool, so it's a monitoring agent. Then we send the data, of course, to a software that's made for storing data, like Prometheus or other time series database. And then, of course, you could visualize your metrics in Grafana or any visualization tool. I make a very quick demo, not of all the stack, but at least a Grafana dashboard, a sample. So it's just about the metrics of one machine. So pretty simple example. We can see that we have the power usage of the machine. So to be precise there, I'll explain that just after, but we are based on a certain technology to have this data. So we miss a part of the power usage of the machine here. And I'll explain that in the next slide. But still, we have a decent part of it, and maybe the most changing part of the power usage of the machine. So that's still interesting to evaluate the impact of software. So this is, as we said, about power usage. Then you can aggregate the data to have energy consumption metrics on a given time frame, whether it's 3 hours to 1 year. Then it's pretty easy to calculate that. And then we can zoom on the power usage of each software. If we zoom on each graph, we see that it's the power usage of each process that's attributed to, that's related to this software. So I won't go into details here. It was just to clarify that my relationship to Rust in this area is also because it seems we can build tools that help us to evaluate our impacts that are pretty low on resource consumption, which is great. So of course it runs on Rust. And to explain a little bit about the data, as I said, we are based on RAPL, so it stands for running average power limit. That's just an interface we have with the CPU, whether it's Intel or AMD, but only x86. That allows us to have power measurements of due to the activity of the CPU and the memory. So that's why I said we miss part of the power usage yet, because we don't have, for example, the power usage of fans or of hard drives, network cards. So most of the time, it's not a very important part of the power usage, but still we are not yet exhaustive at this stage. But the objective of the project is to be more and more exhaustive and to include those as well at some point. One use case of Scaffold, one example could be what the BBC did. They used it to get live metrics of their scope 2 emissions. So we will see just after that what are scope 2 emissions in their OpenStack private cloud to report to the users of their private cloud the estimated greenhouse gas emissions due to their usage. This is a brief overview of the features of Scaffold, but not the point here. Maybe we just can export the data in different monitoring tools or time series database, and we can run it in different contexts. Just remember that the virtualization layer is one of the biggest pain points. So far we can have power measurements in virtual machines, but only on QEMU KVM because we only developed that support at this time. So once again, we could say, okay, that's great. We can build helpful tools with Rust to help us understand our impact, which is part of the reduction process. But let's take a step back. So far, we talked about performance, electricity, usage. So that's interesting. That's part of the topic, but that's not all of it. Let's see what are the impacts of ICT on the environment in a general manner. Then we will have a top-down approach and zoom on different parts. So the last estimations about the greenhouse gas emissions due to ICT in the world, it's more a fork than a fixed estimate. In 2020, it's supposed to be between 2 and 4% of the greenhouse gas emission globally. But what's interesting is the trend, because all of the estimations, they talk about a pretty big increase, so that in 2025 we may have between 6 and 8% of the greenhouse gas emissions in the world due to ICT. So that's not nothing. And more than that, the impacts of ICT are not just about greenhouse gas emissions. In this table, we have some of the impacts, not all of them, but for example, primary energy consumed, that's the first column. Greenhouse gas emissions, that's the second one. GWP stands for global warming potential. Water scarcity, electricity consumption, resources consumption. And when we talk about resources consumption in ICT, most of the time we talk about minerals and metals. So that's the first point. There are multiple impacts. So we'll talk about that just after. The other point is that we see in this table that with those estimations, it seems that the user, the end user devices are the part of ICT that's the most impactful. The other parts in this model is networks and data centers. So from that, we can say that as individuals and IT professionals, we already have a responsibility to extend the lifetime of our devices as much as possible by as less new products as possible, and maybe buy refurbished products, repair our devices, screens, laptops, smartphones, and so on. So that's the first point. And I think it's very important because it includes everyone. It's not just about are we in ICT or are we end users of ICT. It concerns everyone. That being said, maybe there is a scale thing to clarify. We sell about 1.5 billion smartphones a year, something like that in the world. And we install about only, let's say, 20 million servers a year. So the scale are very different. But yet, if we sum up the data from the previous table for data center and networks, so let's say infrastructures that are needed to provide a service, infrastructure still represents 56% of the electricity consumed by ICT, 37% of the greenhouse gas emissions emitted by ICT, and 40% of primary energy consumed by ICT. So it's not nothing, it's pretty important, still important, even if user devices are as well. So as IT professionals, we also have a responsibility on this part, and we could do something on this part. Maybe to clarify a bit things when we talk about greenhouse gas emissions. This is a view about the GHG protocol applied to ICT. GHG protocol is the international protocol that's used in many cases to account for the greenhouse gas emissions and applied to ICT. So here it's a drawing from Microsoft. It looks a bit like that. You have the first scope of emissions, which is the direct emissions in the center. So if you are yourself managing a data center, then you could have greenhouse gas emissions to account for in scope 1, because you have maybe fossil fuels that you burn to make your machines work in the warehouse, or you may have a fuel or diesel generator for as a backup for electricity. So those burn fossil fuels locally. So it's the same as if I was driving a car, I would burn fossil fuel locally. So I emit greenhouse gas emissions locally, which means it's in scope 1, direct emissions. In IT, if you don't manage a data center yourself, most of the time you don't have much to account for in scope 1. You will be much more interested in scope 2 and 3. So scope 2 is about indirect emissions. Indirect emissions, it's pretty simple. My laptop right now is consuming energy in the form of electricity. It's not emitting greenhouse gas emission itself, but somewhere there is a mean to build this electricity that's emitting greenhouse gas emissions. So I'm indirectly emitting greenhouse gases. So scope 2. And scope 3, it's all the rest. And what's all the rest is, it's most of the time what's hidden in ICT. So the first phases of the life cycle of a product, which means extraction of the raw materials, manufacturing, transportation, installation as well. And in the end of life of the hardware, maybe the recycling, which can have an impact as well. And keep in mind that recycling in ICT is very bad, and that's globally. That's not only one country, everyone. So that's one reason more to extend the lifetime of our machines, and lower the number of machines we will throw away. So if we apply this way to account the greenhouse gas emissions to a data center, it could look like this, with a very simple simplification of a data center, but to illustrate. So in green, we have scope 1. So as we said previously, in this example, it would be just the fuel tank and the backup generator that are, let's say, related to scope 1. Scope 2 is in yellow, so all the ICT devices, compute storage network, and so on, are, of course, concerned by scope 2, but also all the other devices that consume electricity, so cooling systems, lighting, fire stop systems, and that kind of thing. The electricity grid is also in yellow, because we will see that after, but you also need to know what's the carbon intensity of the electricity you consume. And then scope 3 in blue, actually it's everything, because everything has been built at some point, so everything has emitted greenhouse gas emission at some point, the building included. And you can see how sometimes it makes evaluating scope 3 emissions hard, and that's maybe why many companies still exclude scope 3 from their carbon reports. That's pretty sad, because even if it's not always known, scope 3 is in many cases the worst part of the impact. So in both in Hubblo and in Boa Vista, we try to base our work and our tools on another methodology than GHG protocol, because for mainly two reasons. The first one is that it's multi-criteria, so we can take into account other impact than just GHG emissions. We talked about that. And the second one is that it makes it forces us to take into account all the steps of the life cycle of a product or a service, where in GHG scope 3, because we put everything in scope 3 at some point, it may blurry a bit the process, and it doesn't help for transparency. And there are many other issues, but let's make it simple. So we base our work on this, and we try to apply this methodology. And if we make the matchup between the two, that's very simple. So scope 3 in LCA, it's extraction of raw materials, manufacturing, transport, installation, end of life, and scope 2 is usage. That's as simple as that. In certain tools or documents, you may find other naming. One is embodied impacts. So embodied impacts is scope 3, so extraction, manufacturing, and so on. And operational impacts, it's usage or scope 2. So let's talk one last time about electricity to be a bit more complete. If we zoom on the data centers consumption of electricity, the estimations today are pretty different. We have estimations of 200 terawatt hour of electricity consumed by data center in the world. We have estimations of 800 terawatt hour of that data center would consume in a year in the world. So wide range of estimations. That's not very surprising, because the data is very hard to get. But what's interesting is that even the estimations that take the lowest hypothesis, so 200 terawatt hour in 2020, for example, most of them, they don't talk about a predicted reduction of the energy consumption. They more talk about a huge increase. For some of them, they predict a multiplication by 3 of this energy consumption by 2030. So those are estimations. We don't know how it will look like in the end, but we know we are not in the right track today, and we have to act on that. It's not necessarily easy, because producing electricity is not a simple process. We have to get energy in another form, which is called primary energy first. We have to transform that energy to make electricity. Then we have to transfer that energy on an electricity network, so that in the end we can power up servers and have applications and so on. In the process, we lose a lot of energy. When we build the electricity, the power generation loses a lot of energy. The transmission of the energy on the network loses some energy as well. When we go in the data center, we are consuming some of this energy. There is an overhead because of cooling, lighting, and other systems. In the machine itself, the power supply will lose energy, and fans will consume some of the energy. In the end, in this example, don't take the numbers for what they are. It's just a order of magnitude. But we could say that most of the time we'll have maybe 10% of energy efficiency regarding the energy that we have actually consumed in its primary form. So let's say when we consume 10 watts for a server, we have consumed actually 100 watts of primary energy in the beginning. To estimate that overhead at the scale of the data center itself, of the building, there is a metric that's called the PUE. You may know it. So it's power usage effectiveness. It's just a ratio between the energy consumed by all ICT equipments in the building and the energy consumed by everything in the building. And the closest it is to 1.0, the best it is. 1.0 PUEs don't exist, but there are some actors on the market that are able to have pretty good PUEs in 1.2, 1.3, or something like that. And we talked before about carbon intensity. So what I presented you just before was about how much energy we consumed. But when you want to evaluate your scope 2 emissions, so scope 2, remember, usage emissions, you need to know what's the intensity, how much greenhouse gas emission I emit for 1 kilowatt hour of electricity produced. And you have some tools today that are pretty nice to have an idea about that, depending on the country where your services are. One of them is electricitymap.org. That's an interactive map where you can zoom on each country, have the electricity mix, and how it's composed, how it's impactful, and so on. It's also an API, so it's pretty nice to for every evaluation process. At some point, it's useful. One word, and then we will move from usage phase, about how we report, assess, and talk about carbon intensity. What I've presented you before, that we could simplify as a big multiplication between the energy consumption of your service and carbon intensity, it's called the location-based approach. It's on the right. That's pretty simple. Emissions of the electricity produced, period. The other approach is called market-based. So there, it's not the emissions of the electricity that is produced, it's the emissions of the electricity that is bought. And that could seem like nothing. It's a huge difference, because actually it's not the electricity that's actually consumed or produced that's taken into account. And you can include in the calculation then market mechanisms like guarantees of origins, renewable electricity certificates, PPAs, and so on. So I won't have the time to go into detail into those notions, but keep in mind that, or at least my opinion is that it's greenwashing, period. And there is much more to say about that, but I won't do it today. And just to sum up about 15 slides about that, because it's a huge topic, it opens the topic to other notions. What I want to emphasize here is, please remember that all of the following terms either don't work in terms of impact reduction or just mean nothing. Everything that's carbon neutral carbon negative, carbon offsets, compensation, green bonds, scope 4, net zero, green energy, green anything, market-based. All of this is just hiding the real problems and hiding behind the market mechanisms to say, okay, my impact is not so important. So then if we step back from usage impacts and we talk about the rest, so embodied impacts. So remember scope 3, extraction, manufacturing, and so on. First, a little zoom, because we talked a lot about electricity and carbon, and I said I want to emphasize that it's not the whole topic. About abiotic resources depletion. So, as I said, abiotic resources depletion in ICT, most of the time it means how much minerals and metals we are extracting from the ground and consuming. I took one number from a French report pretty recent that says in 2020, so I'm not sure, but it's a report from 2022, but the data may come from 2020. But let's say this report says we import in France, just in France, 950 tons a year of minerals and metals in the form of refined metals in and digital products. So when we look at that this way, we could say that's not so much. I could imagine it was much more than that. But actually, what we have to understand here is that when we say 900 and so tons of metals in digital products, it doesn't mean we have extracted 950 tons of materials from the ground. That's way, way far from this. Here you have, so this is extracted from presentation from two experts, mainly Aurore Stéphan, which is a geologist specialized in those questions. So I really encourage you to have a look at her presentations. It's just an extract to give you an idea. This is a drawing of the process from extracting raw materials from the ground to having, I don't know the English word, but a cathode. So just a metal bar that you can send to manufacturers so that they build products after that. And the process is pretty complex. First, you extract the materials. The problem is, in the end, in your metal bar, you need a very high concentration of the mineral. Let's say 99.99%. In this example, we take copper, which is one of the metals we need for ICT and other fields. If you look at the first item on the left, we see that the mineral in the ground is just concentrated at 0.4 to 2%. So we are away from the 100%. And so there is a huge process. Then we need to smash the materials extracted so that we get the pieces of minerals that are more concentrated. This consumes a lot of energy and emits a lot of greenhouse gas emissions. Then there is chemical extraction to get rid of the minerals we don't want and just keep the one we want. We can, one just parenthesis on this. It means that we will get rid of minerals that actually are not interesting, but it also means that we will get rid of minerals that are also interesting to the industries. Because of economic factors, sometimes we lose minerals that are of high value because the mine is not made for those metals and is not intended to extract those metals. So there is a huge loss here as well. And when we say chemical extraction, you imagine that it means a lot of chemical products, and it pollutes the soils, the water, the air, and so on. It leaves full areas, very big areas, and Aurore Stéphan talks very well about that, that are completely unlivable. Many problems around that, I encourage you to have a look. So I closed this parenthesis, but keep in mind that greenhouse gas emissions are far from being the only problem. So then how do we evaluate those impacts, those embodied impacts, whether it's greenhouse gas emissions or abiotic resources depletion or something else? At some point, you need data. What are the data of impacts of a device or a component or something else? So you could have, you could use databases, for example. Unfortunately, there are not so many databases these days. The one that's maybe the most known is Negaoctave, which is okay. I'm a bit late. I speed up. Negaoctave is a very good database in terms of quality. The problem is that it's a paid database. It's not cheap. So what we try to do to make those data more accessible and to democratize evaluation and reduction of the impacts is that we created an open database on GitHub with Boa Vista, which is actually aggregation of the data the manufacturers publish about the impact of their products. We just made them more accessible by having all of them in the same place. Another thing, keep in mind that don't stay stuck on the evaluation of your impact. You can really act on your impact right now by increasing the lifetime of machines, reducing the resources consumed, so reducing the number of machines you need for your services, optimize usage, and so on. Even if the evaluation is not perfect in your company at some point. Then how could we make evaluation easier? There are tools existing. I've presented here mostly open source tools in the center, Boa Vista tools mostly on the right, and the cloud providers carbon calculation tools in the bottom. The tools don't help to evaluate the same thing, so you may have to match some of them to have your evaluation in your context. I just want to show you a very brief demo. I think I have 2 minutes left, I hope. First one is Data Vista. That's the database I told you about before. So you have impacts of devices. For example, if I zoom on laptops, it will give me an average on all the references of equipment we have in the database. We see here that scope 3 in blue is more important. So we see that manufacturing, let's say, is more important than usage in terms of impact. If I go on servers, it will be pretty different as an average, of course, because we talk about machines that run 24/7. We can also see that if I change the carbon intensity for a much lower one in terms of electricity, then manufacturing becomes the biggest part. And I could reduce the manufacturing impact by extending the lifetime. So just I let you play with that after the presentation, but that's a nice tool to talk about those topics and give a first overview. So that's Data Vista. Another thing we did is we made is an API that will give you metrics of impact of your servers and services. Those are not from manufacturers' data. This time, it's based on per die impact metrics. And what's a die? When you build an IT component in the manufacturing process, you have cylinders of metal, of silicium, that you will cut in slice. And those slices, those discs, are called wafers. That's what you see, the big disc you see on the picture. And a die is just a square of silicium that we will extract to build semiconductors. And we can have impact per die thanks to great studies, especially from Germany. And we gathered all those methodologies in the API so that you can just ask questions about your impact and get answers that are pretty nice because, in my opinion, because it includes 3 criteria of impact and not just greenhouse gas emissions. And so it includes abiotic resources depletion and primary energy. But then when you have this API, you have answers, but it doesn't make everything. You still have to collect your own inventory of devices to know what questions you have to ask to the API. And you are still using hypothesis on energy consumption if you don't measure it. So we start other projects on top of the API. One of them is BoAgent. So sorry, I didn't translate that. BoAgent is a tool that will scan for all the hardware specifications of a server, then ask the right question to the API about impacts of manufacturing of the components, and then build the total impact of the machine. On the other side, it will be based on scaffold to have the energy consumption. This way, you can have a global estimation of the impact on all the steps of the life cycle. And I will show you briefly, and then I'm done. One example of dashboard that you could have. Here you have the global impacts of the machine where the tool is running. So embedded emissions, embedded abiotic resources depletion, embedded primary energy consumed, and operational emission, operational abiotic resources depletion, so it's usage. Some graphs about power consumption, and because it's related to a CI pipeline, when you run jobs on this CI, you can have the resource consumption of the job and of the app you are testing, and the estimation of impact per job. So I don't have precise data there, but that's the idea. And is it everything? I had something else, but I think I'm over time. Just keep in mind in one word that we have talked about direct impacts of ICT here and how to evaluate them. But that's not the whole thing. On the bottom right, you see that in 2009, the biggest company in terms of market capitalization were oil and gas companies. And in 2018, it's tech companies. So the trend of increase in terms of market of ICT is huge. And in the meantime, we have never stopped to consume more and more natural resources. So there is it seems there is a relationship between the two. What it is the big question, and more studies to come, I hope. Another thing is, if you heard about sentences like 1 gram of CO2 invested in ICT enables to avoid 10 grams of CO2 that would have been emitted without ICT, or other sentences are ICT enables to reduce by up to 20% of GHG emissions of the other sectors. Keep in mind that those sentences, they come from industrial and companies reports. It comes from consortium like GSMA or JZ. They are consortium of companies that have huge interest in ICT because they build ICT, or ICT is part of their core business model. So be careful with this. There is no scientific paper that says ICT has a positive impact. It doesn't mean it doesn't have one, and it can't have one. Maybe it has a role to play. I just think it has to be defined, and we shouldn't rely on something that's not scientifically based to say ICT by itself already has a positive impact. We don't know that. After that, you have resources. I hope you will have the slides to go further. And I just thank you for your attention.